Yes, sir. We are live on YouTube as well as on Zoom. Good afternoon, participants. Welcome to the live session of the course Introduction to Calculus of Single Variable. Our instructor, Dr. Anupam Priyadarshi sir, is here with us. Please feel free to join in and clear all your doubts. Over to you, sir.
Hello everyone. It was quite good to interact with you finally on the live sessions. So go ahead and ask me if you have any questions.
As of now, nobody
Uh,
joined the session, sir. But we received few queries on the Google form, which we floated.
okay.
Maybe you can
Okay.
start with those
So let
questions.
me.
Yeah.
Yeah. Right. Sure. So the first question from Hitesh. He is writing his profession as a student. So Hitesh asking me, why does every sequence of real numbers necessarily have a monotone subsequence? It is the heart of the sequence theory. So if you have any sequence of real numbers, then how many terms the sequence must contain? It is infinite. Whatever the infinite number of terms there in the sequence, ultimately after many and many numbers, you will find out ascending and descending things. So that means uh, the without any patterns of the sequence, you can ultimately have such a number from where you can find out the increasing or decreasing things. So that's why it is says that every real sequence must have a monotone subsequence. Also, we have a DOS sequence with Hall principle, in which you will have infinite sequence A1, A2, A3, and so on. And for each AK, record two numbers. So the length of the longest increasing subsequence is starting at AK, and then the length of the longest decreasing subsequence starting at AK. By Hall principle, one of these lengths must be infinite. So that means you will have a subsequence. So that subsequence must be increasing or decreasing depending on the sequence given. So that's why every monotone, every sequence, every real number sequence must have the monotone subsequence. And then he writing down. So the reason is that the sequence of real numbers cannot avoid having infinitely many entries aligned on in one direction. By analyzing longs and increasing and decreasing patterns, one can have to extract the monotone subsequence for certainty. Is anyone has joined?
Not yet, sir.
Okay, the second question is from Bindu K, and he's asking about how do we decide which convergence test, ratio test, root test, comparison test is best suited for the particular series? And the second question is, can you share a practical application of these convergence tests outside the pure mathematics? Certainly. I mean, let me give you the answer of the first one, how to decide which convergence test among these one and for the particular series. So if a particular series containing the terms like factorials, exponential or powers, you can go for the ratio test, real numbers ratio test. So simple example is if you ratio like n plus 1 by n simplify nicely for factorials. That's why if the series containing terms like factorials, exponential, and powers, we will do the ratio test. N square, so summation n square by 2 pi power n. I mean, if you take the ratio n plus 1 by n, it will comes out very easily. So it will give you that the series is a converging series. So in that case, where you will find the terms like factorial, exponential, and powers, use root test. Similarly, a root test, what it will give you, it will the terms which are like nth powers. So n pi power and or involving expression that simplify under the nth root. So something like summation n divided by n plus 1 pi power n, right? So such a series where terms are in the nth power, you will go for the root test. And comparison and limit comparison test when polynomial, rational, or simply possible power of n is the nth term of the series, then you go for the comparison or limit comparison test. So simple example is take a series one summation 1 divided by n square plus 3 and compare with n square. So you will easily find out that this series is a converging series. So that's the one thing, intuition, you will go ahead. And what are the applications for the convergent test outside the pure mathematics? There are many. I mean, you have, I believe that you must heard the name power series approximation, where we will find out numerical methods or we will use in the computer sciences. So in the power series approximations, we always use in computer computation exponential x, sine x, tan x, and so on. And the test, the ratio test will give me that the for particular function, the power series approximation is going to be valid for that or not. Because if the series is not convergent, you are not going to use that as a approximation of the function of that series. So you have a function here and you have a approximations here. Approximation containing the power approximation. So containing a number of terms here, and it is in the summation. So if this series is going to be converging series, then you can approximate with this function. Otherwise, so this is the first one. Similarly, you heard the name signal processing, where Fourier series and power series are applied, and in which also the series test is the must one. Similarly, you will have a quantum mechanics, statistical mechanics, perturbation theory, and so on. In the finance, you also have the cash flows in the infinite way or infinite series. So ratio and comparison test confirm if the present value converges or not. Right. So these are the simple real life applications for the series. The next question is by Bhupendra. It is also a student, and see, he said that he asking me Rawls theorem requires specific conditions. What happens if one condition fails? Can we still say something about the function? I believe that in the video we have gone through this question, but anyway, I will love to answer this question. So what is the Rawls theorem? Rawls theorem says that if a function from closed interval a b to r satisfy the three conditions. First condition is if is continuous. Second condition is if is differentiable. If is continuous in a closed interval a b, while if is differentiable on a open interval a b, leaving the boundary points a b. And the third condition is f a equal to b, f. So let me give you one example when each one of these conditions are failed. So first one, f is not continuous in a closed interval a b. Take a simple example, fx equal to 1 when x is less than 0 and minus 1 when x is greater than or equal to 0 on interval minus 1 to 1, closed interval minus 1 to 1. So you will have the 1 and then minus 1, right? So these are the two conditions. Now, f is not continuous at where? At 0, because you have a f1, I mean, close to this one, f0 is equal to 1, and then you have a minus 1. So it is not continuous at 0. So there is no guarantee for the stationary point inside. We are not going to give you any guarantee about the stationary point inside. Still possible that a stationary point exists. Why? Because the function is piecewise a smooth function. We cannot conclude it without continuing. So that's why continuity is essential to apply the extreme value theorem, which guarantees maxima minima exist inside. Similarly, the second condition failed. That means f is not differentiable on open interval AB. Then the most cited example is fx equal to modulus of x on a closed interval minus 1 to 1. So f dash of c equal to 0, you cannot get it. You do not get a point where f dash of c equal to 0. Instead, at x equal to 0, there is a cusp, right? So, this cusp gives you or resembles you the generalized extreme value, extremum value. So Fermat's theorem on stationary point says that the local extrema, which is f dash of c equal to 0, or the derivative fails to exist. So if differentiability is not there, we cannot replace derivative 0 with subderivative containing 0 in non-smooth analysis. And that's why to apply for a Rawls theorem, we must have a differentiability there. Similarly, third one failed. Third, what was the third condition? The third condition is FA is equal to FP. That means the boundary value images must be equal. If it is not equal, take a simple example. So taking a simple example, fx equal to x on 0, 1. So f0 equal to 0 and f1 equal to 1, which is not equal, the Rawls theorem does not apply. So this theorem we will get to apply, we will get to mean value theorem. So in short, if it is not equal, then we have a mean value theorem. And in particular, the Rawls theorem is a particular example of a mean value theorem where both the boundary value are equal. So if it loses the condition, cannot guarantee the extremum value inside those domain. And if loses differentiability, still might have the cusp and corner extremum value, but not a derivative equal to 0. So lose equal drawing points, that is the generalized value of mean value theorem. The fourth question coming from Navneet, who is a faculty, and he's writing, Professor, how can we visualize the difference between Lagrange and Cauchy mean value theorem in real life? Where do these mean value theorem find applications? Thank you, Professor, for asking me this question. Both Lagrange mean value theorem and Cauchy mean value theorems are the cornerstone of the reanalysis. And visualization in real life meaning is quite tough. But let me give you some of the specifications point. So what is the Lagrange mean value theorem? If f is continuous on a closed interval AB and differentiable on an open interval AB, then there exists a point C between open interval A and B, such that you can find out the f dash of C. So that means the slope of the tangent that is equal to FB minus FA by B minus A. So the mean value theorem guarantees at least one tangent to the curve is parallel to the second, right? That is the guarantee for the Lagrange mean value theorem. While the Cauchy mean value theorem, which we need the two function continuous function on a closed interval AB and on open interval AB. So let those functions such that the ratio f dash of C divided by g dash of C is equal to fp minus fa divided by gb minus ga. So that means you have to imagine two curves, y equal to fx and y equal to gx. And Cauchy mean value theorem says that there is a point C where the ratio of the slopes of the tangents equal the ratio of the total changes in the function f and g. So that's how you can visualize that instead of comparing one curve to the x-axis, as we have done in the Lagrange mean value theorem, where we have compared with the x-axis one curve and comparing to the x-axis, we compare here two curves, y equal to fx and y equal to gx, and their slopes, ratio of the slopes of that end. So when the Cauchy mean value theorem reduces to Lagrange mean value theorem, the answer is very easy. If you're taking the second value, gx equal to x, and the first function, then it will give you the derivative of g dash of x equal to 1. So it will reduces to the Lagrange mean value, right? Real life application. So let us give a practical example. I want to move by car from one city to another city, and somewhere I want to see my speedometer at something like 180 kilometer per hour. So whatever the speed you are using from one city to another city, somewhere between these two, there is a speedometer who will tell you at least one time that the car is at the 80 kilometer per hour. So that is the one practical economics rate of changes. So marginal profit to cost ratio, you can use the Cauchy mean value theorem, while average profit to cost ratio, you can also use the CMTVT, right? In thermodynamics, instantaneous ratio versus the overall ratio of any physical quantities like heat, force, or displacement, we can have with the Cauchy mean value theorem. And Lagrange mean value theorem is nothing but it is the particular example where we can find out gx equal to x. So the next question is Varun Kumar, who is a student, and he is asking about how do we distinguish between local and global extrema in a practice when analyzing a function. Good. And why is the second derivative test sometimes inconclusive? And what do we do in that case? The second question is quite important, and I believe that who is listening to this one must be interested in that type. So, if the second test, why is the second derivative test can be inconclusive? Certainly it is. So, take a simple example: fx equal to x to the power 4, and take first derivative. What will be the first derivative? That is equal to 4x cubed. And what will be the value of the first derivative as 0? It's 0. What is the value of the second derivative at the point 0? It is 0. So that means you are not, it must be inconclusive. But no, whenever you draw the function fx equal to x power 4, you will find out the local max, local minima at 0, right? Similarly, if you take the example fx equal to x cube, again the first derivative at 0 point is 0, the second derivative at 0 point is 0. But 0 is a point of inflection. It's not an extremum point. It's not going to give you the maxima or minima. That's why the second derivative test can be inconclusive. It's not going to be conclusive, right? So the two example fx equal to x to the power 4, where you will get the local minimum at the second derivative value is 0, and where fx equal to x cube, where the second derivative is 0, but you are not getting any extremum point. That will become a point of inflection. That's why the second derivative test cannot be a conclusive. It must be a inconclusive. And the first one, how to distinguish between the local extrema and the global extrema in a practice by analyzing a function. So what is the local maximum? Whenever we use the term local, that means you are working or you are talking about the neighborhood, right? So you are taking the point x and then x minus epsilon to x plus epsilon. That's the motive of this one. So local extremum is something, it is greater than or less than, depending on extremum value and the value we are taking, right? So but in a global, your domain is not going to be local now. It is going to be a full one. That's overall the things. So a point x equal to c is a global maxima if fc is greater than equal to fx for all x in the domain where the function has been defined. So what will be the practical approach? Okay, so firstly find the critical points f dash of x equal to 0, solve that expression, and it might be possible that f dash of x is undefined. Classify the local behavior. How we can classify? By taking the second derivative f double dash of x, and whatever the x, the value of the x you have obtained from the first derivative, put that there here. You will find out less than 0 or greater than 0. If it is less than 0, that is maxima, local maxima. If it is greater than 0, it is the minimum, right? So check boundary of the domain and compare all over with the boundary and the second derivative and the all local maxima, local minima. That will give you the global maxima. So on a closed interval, let's say closed interval AB, global extrema always occur either at a critical point or at the end points of the domain. So that's why you can have the practical approach about the local and the global extrema. And Murli sir, there is no other questions. So if anyone has joined, I will love to see them.
Yeah. Thank you so much, sir, for answering all those queries in a very detailed manner with a lot of examples. So far, nobody turned out.
Okay.
Let me just check on the YouTube, sir, whether any. No, sir. On YouTube also, learners are not watching. Maybe we can wait for a minute or two. If
That's sure, certainly,
no,
certainly. I have, I
yeah,
have. Okay,
sure,
no
sir.
problem
If
at all.
nobody is turning out, then we will end the session soon, sir.
Sure,
And
certainly.
apart from these questions, would you like to discuss anything in general, sir, related to our course?
Yeah, I mean, this course is, I mean, I am teaching here in Banaras University, and fortunately, this semester I am teaching any in NEP courses calculus of several variables. But before going to the calculus of several variables, we will introduce the calculus of a single variable, and that is the motto of this SWAM BHU INA course. So in this course, as you can see, we have started with the sequence. So sequence is nothing but it's a function. So that means whatever you have learned in 10, 11, and 12, I will just going to give you a generalized version of that one. So you are in a somewhere in coaching or somewhere in tuition where you will find out, okay, how to find out the limits of a function. And you will just go with the type 1, type 2, type 3, and so on and so on. Here, what we are going to give you, it will give you the generalized definition of the limit of a function, or you can say limit of a sequence, because every sequence is just a function having the domain natural number. That's all. Any function. And how you can visualize your function? So if you want to get the function in a one point or in a one line, you will just see or observe the property of a bundle of arrows. So that's why mathematician use as a function as an arrow. So what will arrow do? So if you have a two arrow and if you want to strike it, the arrow will strike at a one point. It may be possible that the two arrow may strike at the same point, but it never possible that one arrow strike in the 2 points. So that is the difference between a function and a relation. If one arrow strike at a 2 point, that is not a function, that will be a relation. So once you have the function, then you will go with the sequence, and then you get the limits of a sequence in a generalized way. So the course from week 1 to week 12 is totally based on that one. I mean, once you go through all the videos, you will find out that each one video has linkage with the previous one, and that is the whole motto of this course. I totally believe that this course will help you at least in a calculus of single variable.
Thank you so much, sir. Since nobody have joined, can we wind up the session, sir?
Yeah, I mean, anyone who can listen this can mail me or can ask me by giving, I mean, message to SWAM BHU or something to directly to write to me. My already emails and all those on the websites. So one can go through it and ask their queries. I will be happy to answer them. So thank you, Murli sir.
Yes, sir. Thank you so much, sir, for this live session. It was very informative and helpful. We hope our learners watch the recorded session and benefit from it. So we are closing
Thank
the
you, sir.
session now. Thank you, sir. Thank you, sir.
Thank you. Thank you.